Hi boys and girls. Today we begin the Unit 4 lectures in which we will be discussing further applications of differentiation. Today's lecture 4.1 and the topic increasing and decreasing functions and the first derivative test. First of all, let's start with a couple of definitions. What does it mean when we say increasing and decreasing functions? A function is increasing if, as x moves from left to right, its graph moves up. Now, this is not earth-shattering news. We would probably intuitively understand that if we saw a graph moving up from left to right, we would say it's increasing on that interval. A function is decreasing if, as x moves from left to right, its graph moves down. Again, this is something that we would probably intuitively understand by looking at a graph. But now we're going to use the first derivative to test for increasing and decreasing functions. Let f be a function that is continuous on the closed interval ab and differentiable on the open interval ab. If f prime of x is greater than 0 for all x in that interval, ab, then f is increasing. They're saying if the first derivative is greater than 0, positive, then the function is increasing there, and that makes sense. The first derivative being positive means that the slope is positive, and we would expect to see an increasing function. If f prime of x is less than 0 for all x in AB, then f is decreasing on that interval AB. Once again, if the first derivative is less than 0, that means the slope is negative, and so we would expect to see a decreasing function there. And then finally, if f prime of x equals 0 for all x in an interval, then the function is constant. We know that when the slope of a line is 0, we would have a horizontal section of the graph or a constant section of the graph. So using this information, we're going to be able to determine increasing and decreasing intervals on a function. Let's take a look at this graph and continue this discussion, analyzing a curve using the first derivative. Notice this section of the graph right here is decreasing. What we can expect to find is that the first derivative will be negative, less than 0. That will analytically indicate that this section of the graph is decreasing until it reaches this particular moment in time. This is an extreme value, a minimum value, and there will be a moment at which the slope is 0. Of course, the tangent line here is horizontal, and we would expect the slope of that line to be 0. And then, of course, it segues back into an increasing section of the graph where we would expect the first derivative to be positive. Then once again, it's reaching an extrema, a maximum value, where for a brief moment we have that horizontal tangent line. The slope would be 0 there. And then, of course, it continues on into negative slopes. Now, this is a non-differentiable point on the graph, but I used this particular graphic because it gives us a constant section of the graph as well. Obviously, the slope at all of these points on this section would be 0 because it's a horizontal line. Now, imagine that you don't have the graph. You just have the function, and you would be able to use information about the first derivative, where it's negative or positive or 0, to determine intervals of the graph and where they are increasing and decreasing or possibly constant. So this leads us to guidelines for finding intervals on which a function is increasing or decreasing using the first derivative. Let f be continuous on the interval ab. To find the open intervals on which f is increasing or decreasing, use the following steps. First, locate the critical numbers of f in the interval ab and use these numbers to determine test intervals. We learned how to find critical numbers in the last unit. Those are the places where the first derivative is equal to 0 or undefined. But notice how these places where the first derivative equals 0 divides the graph into segments. Segments where it's decreasing or increasing or constant possibly. So those critical numbers will give us sections of the graph to examine. Those will be our test intervals. Then determine the sign of f prime of x at one test value in each of the intervals. Once we know where the critical numbers are, we can find a test value within that interval and find out what the first derivative is there. If it's positive, that means we have an interval on which the graph is increasing. If it's negative, that means we would have an interval on which the graph would be decreasing. Of course, if it's 0, that would mean we would have a section of the graph which is constant. Then use these results to determine whether f is increasing or decreasing on each interval. All right, I think it's time to practice. Find the open intervals on which f of x equals x cubed minus 3/2 x squared is increasing or decreasing. Remember, our first step is to find the critical numbers, so we'll need to know what the first derivative of this function is. Let's find that. F prime of x is equal to 3x squared minus 3x. To find the critical numbers, we set the first derivative equal to 0. And then I'm able to factor out a 3x, which gives me two factors, 3x and x minus 1. Each of these will generate a critical number. 3x equals 0 gives me one critical number at 0, and x minus 1 equals 0 gives me another critical number at 1. Now we know for sure that these are the critical numbers of the function, therefore we're going to use those critical numbers to set up the test intervals on which we determine if the function is increasing or decreasing. This function is a polynomial and it's defined on all real numbers. So I'm going to set up my intervals this way, from negative infinity to 0, then from 0 to 1, and then from 1 to positive infinity. These critical numbers define the sections of the graph I need to look at. I'm going to find a test value in each of these three sections, find the first derivative at those test values, and that's going to tell me if the function is increasing or decreasing in that section. Since I want to keep my numbers small, and integers are nice as well, I'll choose -1 for my test value. Here I have to use a fraction, so I'll choose 1/2. And over here I'll choose the number 2. That's supposed to be positive infinity, by the way. All right, I need to know the first derivative value at each of these test values, so let's find that. F prime of -1 is going to be 3 times -1 squared minus 3 times -1. That ends up being 3 plus 3, which is 6. It doesn't so much matter what the number is. What's more important is that it's a positive number, which means the function is increasing on this interval. Now let's find the first derivative at 1/2. That's going to be 3 times 1/2 quantity squared minus 3 times 1/2. This gives me 1/4 times 3, which is 3/4, minus 3/2, which gives us a -3/4. Again, not so important what the first derivative is, but the sign is important because that tells us that the function is decreasing on that interval. And finally, let's look at the first derivative at our third test point, which is 2. 3 times 2 squared minus 3 times 2 gives us 12 minus 6, which is 6, another positive number, which tells us that the function is increasing on this interval. Now let's take a look at the graph and see that it verifies our analysis. Notice that from -infinity to 0, we have an increasing section of the graph, which is what we found. Then from 0 to +1, we have a negative section of the graph, a decreasing section of the graph, which is matching the analysis that we found. And then from +1 to infinity, we have an increasing section of the graph, which also matches our analysis. This is how we use the first derivative and critical numbers to set up intervals in order to determine which sections of the graph are increasing and which sections are decreasing. The first derivative test. Let C be a critical number of a function f that is continuous on an open interval I containing our critical number c. If f is differentiable on the interval except possibly at c, then f of c, the function value there, can be classified as follows. If f prime of x, our first derivative, changes from negative to positive at c, then f has a relative minimum at that point. If f prime of x changes from positive to negative at c, then f has a relative maximum at that point. If f prime of x is positive on both sides of c or negative on both sides of c, then f of c is neither a relative minimum nor a relative maximum value. What does this mean? We know that setting the first derivative equal to 0 gives us our critical numbers, and critical numbers are the places on a function where potential extrema occur, possibly a maximum or minimum value. But which is it? Remember, the idea here is that we're not looking at the graph, we're using the first derivative and the analysis involving the first derivative to determine what's happening with the function. So how can we use the first derivative to determine whether or not something is a max or a min value? We can look at the first derivative on either side of a critical number and determine if it's a max or a min. For example, let's say that we have a critical number here, and let's pretend like we don't know if it's a max or min. It turns out that if the sign of the first derivative changes from negative to positive, meaning we're going through a decreasing to increasing section of the graph, that critical number must be a minimum value. Similarly, if we have our first derivative changing from a positive to a negative number, meaning we're going from an increasing section of the graph to a decreasing section of the graph, then that critical number must be a maximum value. So once we have the critical numbers, we examine the first derivative on either side to determine whether that critical number is a max or a min. If we have a critical number and we look at the first derivative behavior on either side and see that it goes from negative to negative, or it goes from positive to positive, not changing sign, then we haven't gone through an extreme value. It's neither a max nor a min. So that is how we use the first derivative and looking at behavior on either side of a critical number in order to determine what type of extrema we have, if it's an extreme value at all. Now we have an opportunity to apply the first derivative test. Find the relative extrema of the function f of x equals 1/2 x minus sine x in the interval 0 to 2 pi. Notice I have the graph of the function here. I've also sectioned off the interval that we're looking at, and I have some little tools to help us with our trigonometric issues. Of course, to find relative extrema, we're going to need the first derivative. So let's find the first derivative of this function. F prime of x is equal to 1/2 minus cosine x. To find critical numbers, we set the first derivative equal to 0. 0 equals 1/2 minus cosine x means we're looking for places where cosine x equals 1/2. Now, we have to remember that 1/2 comes from the 30, 60, 90 triangle. So if this is a 30, 60, 90 triangle, then the sides are 1, 2, and the square root of 3 accordingly. Which angle, 60 or 30, has a cosine of 1/2? Cosine is adjacent over hypotenuse. The 60-degree angle has a cosine adjacent over hypotenuse of 1/2. Now, there are two places in the interval from 0 to 2 pi that has a positive cosine. Remember, we have the 60-degree reference angle here, we have it here, here, and here. It turns out that cosine is positive in the first and in the fourth quadrants, where the adjacent side is positive. So that is going to be pi over 3 in the first quadrant and 5 pi over 3 in the fourth quadrant. Now, these are our critical numbers, and here's how we're going to set up our interval. We do have a closed interval, so we're going to start at 0, and we're going to go to pi over 3 here. Then we'll go from pi over 3 to 5 pi over 3, and then finally 5 pi over 3 to 2 pi. Now, once you have these intervals, you can see that the function is decreasing, then increasing, then decreasing, but we're definitely going to use our analysis. We'll need test values in each of these intervals. From 0 to pi over 3, I'll use pi over 4. From pi over 3 to 5 pi over 3, I'll use pi. And from 5 pi over 3 to 2 pi, I'll use 7 pi over 4. Both of these reference angles are 45-degree angles. We're going to need the first derivative at each of these test points, and then we'll need to know whether it's increasing or decreasing. This should actually say increasing / decreasing question mark, which you'll know once you have the sign of the first derivative at each of these values. So let's find that information. What's the first derivative at pi over 4? At pi over 4. That's going to be 1/2 minus cosine of pi over 4. Well, cosine of pi over 4 is the square root of 2 over 2, or 1 over the square root of 2. 1/2 minus 1 over the square root of 2, even if you don't know exactly what that number is, it is a negative number. That tells us that this interval has negative slopes, meaning it's decreasing there. Now let's find the first derivative at pi. This is going to give us 1/2 minus cosine of pi. Cosine of pi is -1. 1/2 minus a -1 gives us a positive 1.5, which of course is a positive number. And that means the slopes are positive on that interval, meaning it's increasing there. And then finally, let's look at f prime of 7 pi over 4. And we're going to have 1/2 once again minus 1 over the square root of 2, because that's a 45-degree reference angle. Another negative number, which tells us that in that interval we have a decreasing function. Now, using the first derivative test not only means that we're finding the critical numbers, we're determining which intervals are increasing and decreasing, but furthermore, let's use our analysis to determine whether the critical numbers we found are maximum values or minimum values. Pretend like you can't see the graph and you don't already know. Let's look at the sign of the first derivative on either side of each critical number. Pi over 3 is one of our critical numbers. Notice the first derivative goes from negative to positive there. That means it goes from decreasing to increasing, meaning this has to be a minimum value. Over here at 5 pi over 3, our other critical number, the first derivative goes from positive to negative, meaning it's going from increasing to decreasing. That means 5 pi over 3 has to be a maximum value. This is the first derivative test, examining the sign of the first derivative on either side of the critical numbers so that you know that the critical numbers are max or min values. Yes, the graph verifies our analysis, but if we didn't have this graph, we would also be able to use this information to know what kind of extrema we have. In our last example, we're once again going to apply the first derivative test in order to find the relative extrema of the function f of x equals the quantity x squared minus 4 to the 2/3 power. Of course, we'll start with the first derivative, and notice that we'll need to use the chain rule for this derivative. We're going to have 2/3 times the quantity x squared minus 4 to the -1/3 power times 2x. This can be written as 4/3 x times x squared minus 4 to the -1/3. And now let's drop this quantity to the denominator along with this 3, giving us a final derivative of 4x over 3 quantity x squared minus 4 to the 1/3 power. Now we know that we'll find our critical numbers by setting the first derivative equal to 0 and by also determining where the first derivative is undefined. Setting the first derivative equal to 0 means we need to look at where the numerator is equal to 0, and that gives us a critical number of 0. But notice because of this denominator, we are also going to have places where this first derivative is undefined. Wherever the denominator is 0 is going to generate those values. So let's set the denominator equal to 0 to determine where the first derivative is undefined. That should be a 4 by the way. It kind of looks like a 9. Distracted me for a moment. Dividing by 3 and cubing both sides will keep this a 0, but that's going to give us x squared minus 4 equals 0. And then that means that we have two places where the first derivative is undefined, at plus or minus 2. All three of these numbers are critical numbers. So let's set up our test values. From negative infinity to negative 2, then from negative 2 to 0, from 0 to positive 2, and then from positive 2 to positive infinity. Picking test points in each of these intervals, I'll have negative 3. I'll use negative 1 here, positive 1, and positive 3 here. I need to know what the sign of the first derivative is at each of these values. So let's do that. F prime of negative 3 gives us 4 times negative 3 over 3 times negative 3 squared minus 4 to the 1/3 power. Now, I'm not going to calculate the actual value, but let's look at the sign of the numerator and denominator. This is negative 12, so it's going to be negative in the numerator. In the denominator, 9 minus 4 is 5 to the 1/3 power, some positive decimal times 3, a positive number. That means we get a negative value at negative 3. The interval is decreasing. Now let's find the first derivative at negative 1. We'll have 4 times negative 1 over 3 times negative 1 squared minus 4. All of this raised to the 1/3 power. Again, let's focus on the sign of the answer. The numerator is negative again, 4 times negative 1, and negative 1 squared, positive 1 minus 4, is a negative number. The cubed root of this negative number, negative times 3, negative number, negative over negative is positive, which means in this interval our function is increasing. Now let's do the same for positive 1. 4 times 1 over 3 times 1 squared minus 4 to the 1/3. A negative number to the 1/3 power is negative times 3, negative in the denominator, but positive in the numerator. So now I have a negative sign, which means the function is decreasing in that section. And finally, let's look at the first derivative at 3. We're going to have 4 times 3, and then in the denominator, 3 times the quantity 3 squared minus 4 to the 1/3, a positive number over a positive number, which gives us a first derivative which is positive, meaning that the function is increasing in that interval. So let's examine this data and sort of analyze what's happening. Remember that in the original function, we have no undefined values. So it's continuous on all real numbers. There are no asymptotes or odd places occurring. It wasn't until we looked at the first derivative that we saw that we had some non-differentiable points at 2 and negative 2, but it's still continuous there. So if I were guessing, I would say that as we look at negative 2 and positive 2, I have a decreasing function that is coming down to a non-differentiable point. So maybe it's a sharp point or something. Then the function begins to increase, and since this is a critical number, it is differentiable here. Maybe at 0, it's a maximum value since it's changing from positive to negative. And then it's coming back down because in this interval, it's negative to a non-differentiable point, which probably is a sharp point, and then it begins to increase again. Now, using the first derivative test, we can say that at negative 2, this critical number, even though it's not differentiable here, it still can be a max or min value. Since we're going from negative to positive, we know that it's a minimum value. The function is decreasing and then increasing there. At 0, we have a positive to a negative, increasing to decreasing, meaning we have a maximum value there. And then at positive 2, the first derivative goes from negative to positive, decreasing to increasing, another minimum value. So notice how I've used my analysis and my knowledge of what the graph might look like just to get a general idea. Now let's look at the actual graph. We're going to see that the graph verifies our analysis. There it is. We have this decreasing section. It's continuous and defined here, but it's non-differentiable. You can't find a derivative at that point. And then it goes smoothly up through the critical number at 0, which is a maximum, negative values, another non-differentiable point, and then increasing. This is still a minimum value even though it's not differentiable. So there you have it, applying the first derivative test. That's it for today's lecture. G.K. Chesterton said, "It is possible that God says every morning, 'Do it again,' to the sun, and every evening, 'Do it again,' to the moon. The repetition in nature may not be a mere recurrence, it may be a theatrical encore. Every day, God's masterpiece, creation, is on display for you and me. I pray that we are an appreciative and enlightened audience. God bless you, boys and girls."